Okay, even least square method is one of the approach that you can use to find the best linear regression model that fit with your data. Of course, there's some disadvantage with this technique. Okay, so one of the disadvantage is that I have been highlight in general is that if you go to the equations there, you can see that here one things that for sure that is very hard for to be produced is this what we call as a normal equation. If you see the normal equation there, there's a okay, the one problem with this normal equation is that the one of the operation involved here is inverse matrix, which is this one. Okay, this one, inverse matrix. Okay, if you remember this x here, what is your x there? Capital X. Your capital X is this. Okay, you can see here for least square method, it's one of the disadvantage if the data is too big. Like I mentioned, for example, let's say we are using the size of 1000 samples. Okay, if you talk 1000 samples, meaning that the dimension going towards this one, okay, this x over here is 1000. Okay, so you can imagine if you talk about this normal equation, this x over here, if the dimension going towards transpose is going to that transpose, okay, because we have a transpose and non-transpose over here, meaning that this one, okay, let's say your ST is okay, one again the sample number of sample is 1000, meaning that your column over here, if you transpose the x, will become 1000, and then you are multiplying with another matrix of your x where it's going to 1000. At the end, the produced matrix should be 1000 times 1000, meaning that this xtx is actually the size is 1000 times 1000. Okay, so imagine if this matrix is the matrix is so big enough, it's very highly computational expensive. Okay, it's a highly computational expensive if you want to compute this one, if you want to compute the inverse operation of the big matrix. So that's why least square method is not practical in order for you to find the optimum beta or the optimum parameter if the data set is very big. It's not big, okay, 1000 is not big, but still 1000 is enough that can make the your computer is required high computational time, okay, or require more computational time to perform the inverse operation of this big matrix. So that's why one of the alternative to do this optimization, or we are doing the hyperparameter tuning, or in other words, this is what we call a training operation lah. Okay, this is about the training operation. When we talk about optimization, it's actually the it's also called as hyperparameter tuning. It's also called as a training operation, because that is the one that we want to do in order for you to find the best parameter, the best beta that you can have to represent or to produce the cost function which is as minimum as possible. Okay, so that's why one way to solve this one is what we call as, we are using what we call as a gradient descent algorithm. Of course, this is one of the old technique to solve the least square method. Okay, again, if you learn about the new modern technique, they have a lot of things such as Adam optimization and so on, but in this syllabus we only talk about the gradient descent algorithm. Okay, of course, when you learn and when you do some project, you can apply any optimization mechanism, but this is one of the optimization approach in order for you to find the best beta that can produce minimum cost function value. Okay, so again, that's why I would like to highlight this thing before we start to talk about the advanced things such as artificial neural network, because you can see that that is the history behind this thing. Of course, what we have covered before when we talk about the least square method, that is only applicable for small data. But if you want to apply the linear regression, not just ANN, if you want to apply the linear regression with the big data, okay, the more data, then actually the algorithm they are prefer is not least square method anymore, okay, because least square method there's no iterative, okay, there's no iterative behavior, okay. You just simply take the take this equation, okay, like you do before. You just take this one, okay, you just take this one, you just list up all the operation, then you multiply, you sum together before you can get your M. Okay, there's no iterative behavior. But in almost all optimization, the existing optimization start from the gradient descent algorithm. Later you see that there's an iterative operation where actually you are searching for the minimum value, meaning that there's an iterative like this. First you set this one, then it become this one, then it become this one. At the end, they find out this is the minimum one. Okay, from here then they going towards the minimum value iteratively. There's a for loop approach there. Okay, so that's one of the common way to optimize your linear regression iteratively, is actually through the linear regression. Okay, because that is where they always try to find the best beta for your linear regression model. Okay, so this is the same thing. Actually, the basic search optimization here is actually referred to this thing. Okay, what we have learned later, which is called gradient descent algorithm. Okay, like I said before, the basic search actually is this is where the mechanism look like. For example, you start here. That's why what I want to highlight here, most of the iterative searching for optimization, doesn't matter is it the gradient descent or the modern optimization like Adams optimizer and so on, they always start with some random numbers. That's why you can see initially you will start the beta here. Okay, it's random. Okay, when you start, you just start with a random number, and you find out it will do some iteratively, and actually it's a guided searching, meaning that it will keep guide how to minimize how to find the best B, which way to go, so you can find the value here or the minimum value here. Okay, so that is how the gradient descent work, or that is how the existing or the latest optimizers such as Adams work. Okay, meaning that they behave iteratively to search and find which actually the optimum value, or in this they also use the word converge, or to find the convergence. When you say to find the convergence or converge, is actually is a minimum value where you get your beta that's producing the minimum value, that producing the minimum cost functions value. Okay, so this is the basic thing. First set to initialize, and then you do some iterative process. Okay, it's different. That is a significant difference between this thing and the least square method, because least square method you don't have any iterative mechanism there. Okay, now let's go to the gradient descent algorithm. So this is how it look like. You can see that the concept is similar. You need to initialize your B, okay, your beta. So for example, this one, your beta. Okay, you can see that the behavior of gradient descent algorithm is similar to the common one, which is this one. Okay, again, like I said, the difference is just the recent optimization. There's they have their own way how to update the betas there. But if you talk about the gradient descent algorithm, this is how it should look like, meaning that same, you must to initialize your b or your beta with certain numbers. Okay, that's why in most of the algorithm we just put a random number to set with your to set to your b or to your beta. Okay, whether it's you must set your beta 1, beta naught. If you talk about one variable example, if you have a multiple, then you need to initialize all beta naught, beta 1, beta 2 up until your beta d. Okay, you must give some numbers, some random numbers as a initially you need to do that, and then you need to repeat updating your betas there. Okay, this is your old beta. Okay, from this equation you can see this is your old beta, and then your old beta must minus with the partial derivative of your cost function and that beta. Okay, so this is that's why the difference between this one is you can see this is your tau, this is tau plus 1, meaning that this is the process of updating your beta, means that let's say your beta naught here initially is equal to, let's say, 0.8. okay, but at this position, let's say this is your beta naught. So if your beta naught currently is equal to 0.8, okay, and then you must minus, let's say you do this operation and you find out that this one is 0. Let's say 0.01. Okay, so in other words, you will update your beta naught. Your new beta naught now is equal to, okay, I just put beta naught new. Okay, your beta naught new is equal to 0.79. Okay, so that's how you will keep update your beta like that. Okay, not just beta naught. If you talk about the one variable example, you must update your beta naught as well as beta 1, and then it depend on how much your variables. If you talk about more variables, then it depend. You have beta naught, beta 1, beta 2, you will do the same. You will keep updating your beta naught, beta 1, beta 2 up until your beta d. So that you will do in the gradient descent algorithm. Okay, you will do until the convergence. So how you know the algorithm is keep convergent? How you know actually whether your system is converged or not? It's depend on, there's a many approach. Okay, recently they proposed in order for stop this looping, what we call as a stopping criteria. Okay, or the stop iteration, stopping criteria. Okay, there are many techniques to do some what we call as stopping criteria. Okay, meaning that how to stop this looping when you find out it's already converged, or it's when the convergence happens. Okay, one of the old technique is that you just compare between your old beta and the new beta, meaning that if the new beta and the old beta is not so much changing, or the changing is very small, then you can stop the process of iterative or repetitive operation like this. Okay, that is I think can be considered one of it, the old one, means that if the update version of your beta is not so much change, or meaning it's not changing anymore, then you can stop you can stop the updating process, or the repetitive process like this. Okay, so I don't want to highlight on that. Okay, that is one way, but in general this is how it's work, meaning that you need to initial the beta, and then you will do some iterative mechanism to search going towards the negative value. Again, this is like the one I draw before. Okay, if you draw the cost function, okay, again this one is a bowl, but we just take a cross section. Okay, if you plot the cross section of your cost function, and then you will find out that by having this mechanism, okay, initially, let's say you set some of your beta is equal certain number, might be that will produce the value at this point over here. Okay, and then at the end it will keep updating, okay, based on this finding this partial derivative between your cost function and with that beta, and you multiply with this constant. This is actually called as learning rates. Okay, it's a learning rates. This one will tune how fast it learn and how slow it run. If you set it, the value is bigger, then it will keep, you know, the learning process is fast, and if you keep the value is small, then the learning process is a little bit slow. But there's a disadvantage, you know, you cannot set the learning rates very big, and you cannot also search set the learning rate or the alphas there with a small number, because small will make the searching process or the stepping process, you know, jumping from here to here is very small. Okay, if you want going towards that value, if you put the alpha which is small, then you need to keep more iterative, more repetitive operation to arrive at this point. Okay, again, this is the point we want to arrive. But if you put the learning rates bigger, then the jumping process is a little bit bigger. Let's say if you put the alpha there bigger, then it might step something like this, you know, it's going to that, it's going to that, it's going to that, it's going to that direction. At the end, you will find out it will jump and static like that. Okay, so once the stepping okay, that is another terminology that you can imagine. If you put the alpha there bigger, meaning the stepping process or the stepping size is become bigger. So if it become bigger, at the end, you know, when we talk about the stopping criteria that I mentioned before, if your beta, okay, is only produced, there's no changing at all, it keep repeating this again and again, and until, you know, of course, when you set your repetitive or iterative operation, you will set the maximum. There's a set the maximum iterative operation. Let's say you want to keep looping this one. If not going to converge, it will stop at 1000 cycles. Okay, it will, of course, when you imagine that your learning rate is become, okay, you set with the biggest number, then it will keep searching. Okay, and then it will stop here, and then if your operation or the repetitive operation here is arrived at 1000, it will stop, let's say here, then it will just take this value, this beta. Okay, just take that beta as your the optimized beta. So in other words, that is the disadvantage of setting the alpha which is with the biggest number. Actually, when you have the biggest number, then you might not know actually the global minimum or the minimum you can arrive actually is going down here, but you cannot search for that because your jumping is too big. You cannot go into this small valley over here. So that's why that is the disadvantage of setting the alpha with higher value. Okay, so but in order for you to arrive at this value, then you need to set your alpha with the smallest value. But the drawback is that, or the disadvantage of that is that you need to, you know, the learning process is quite slow, and is required high computational time to execute that one. Okay, then again, this is just some derivation of your cost function, because again, if you see over here, still in gradient descent algorithm, you need to know what is your delta cos delta j over delta beta. So how to obtain that one? Of course, this also come from the previous definition of all things there. And then I don't want to highlight this one, but at the end you can see that this is how it's look like. Okay, at the end, okay, this is how it look like, meaning that this thing, if you do some derivation later, you will find out, if you talk about the linear regression, it will end up that actually this is how it update your beta. Okay, your beta is your beta over here can be update. Okay, this one we use a symbol arrows there, meaning that assign. Okay, meaning assign. What meaning is by assign that if you have the old value here, then you do the operation with this one, then you assign the whole thing here with this one, meaning that this beta become the new beta by updating your old beta with this value. okay, minus this one, meaning this is what we call as a beta updater. Okay, some people call this one as updater or parameter updater, because it will always update your beta. Okay, updater. Okay, later when we learned about ANN, you also call this one as updater. Okay, it's a parameter updater or the beta updater for this one. But because later when we learn ANN, we don't call beta anymore, we call as a W, then this one become a W updater. Okay, just the different notation, but the concept is similar, the formula is similar. So but I just want to show you here is that when we talk about the gradient descent that happen for linear regression, this is what we do, meaning that in order for you to update your beta, then you need to get your predicted this one again, this is your predicted y. Okay, predicted y, yi. Okay, of course you need to get all the predicted one. Okay, of course this one is your e, if you remember, this is your e. Okay, ei means that e1, e2 and so on. You must multiply your e with your x here. Okay, the input of that samples. Okay, if you remember this, the I and j, because the I represent the sample, j is actually your index for your dimension. Okay, meaning that every error you must multiply with the input value, then you sum up together, you multiply with your alpha in order for you to get your updater for each and every, meaning that you need to proceed this one for each and every beta. Okay, meaning that if you have two beta naught and beta 1, then you need to proceed these two. Okay, so that's how the gradient descent algorithm works. But I don't want to highlight on this thing, because later we will have a long discussion about the gradient descent for ANN, which is similar to this one but more complicated, because the expression now is become more and more bigger, and then the derivation or the partial derivation operation is a little bit complicated as compared to the gradient descent algorithm happen for linear regression. Okay, this one I just want to highlight is that later I hope that when we learn about ANN after this, you don't feel so shocked. Okay, when you heard about the gradient descent algorithm, okay, why people introduce the gradient descent algorithm at the ANN is because the gradient descent algorithm is also applicable. It have been practiced in finding the optimum value in linear regression equation. So this is what I just want to show. So later then you realize that the gradient descent is not exclusively for ANN, but actually is also have been used for linear regression, because to solve the disadvantage of least square method that cannot cater the high number of data. Okay, if you talk about training the highest number of samples, then if you want to choose a linear regression, then it's impossible or impractical to use a least square method. Okay, the system, or it doesn't matter you are using MATLAB or Python, they always use the gradient descent algorithm in order to find the best linear regression model that fit with your algorithm. So this is the concept.